about the past year. And so today, indeed, I will share with you some of the work I did in the past years for my PhD project. I won't go through it all, no worries. I'll just highlight a few things about my work on what's called, my thesis called Development of Reduced Order Modeling Methods for Incompressible Flows with Heat Transfer and Parametric Boundary Conditions. So what I will do, I will shortly explain you the background and motivation of my PhD project. And then I will go with you through some of the reduced order modeling methods that I developed and 2 cases that I studied. In the end of this presentation, I will conclude with a short recap. So if you have any questions and you think it's better not to wait till the end, this presentation, feel free to interrupt me, that's totally fine. So I carried out my PhD project in collaboration with SCKCEN. So SCKCEN is the Belgium Nuclear Research Center. And SCKCEN is developing a multifunctional experimental radiation facility named MIRA. So MIRA stands for Multipurpose Hybrid Research Reactor for High-Tech Application. So on the left, you see a cross-section of the reactor. So over here, so basically you see here what they call the primary cooling system. So the MIRA facility consists of a pool type reactor containing a core that's cooled by molten lead bismuth athetic, which is a heavy metal alloy. So with regard to the thermohydraulic design and safety assessment of the primary cooling system, a major challenge is characterizing the complex transport phenomena in the coolant flow field, such as local flow mixing, natural convection, that's driven by buoyancy, thermal certification in, let's say, the lower plenum and the upper plenum of the reactor. So MIRA and other what they call next generation reactors require therefore extensive computational characterization in order to adequately perform the safety assessment of the primary cooling system. So in the nuclear industry, everything is about safety. So that's why they do all these computational simulations. So so there are 2 types of numerical codes that are frequently used for the thermohydraulic analysis in the nuclear industry. And the first type of codes are based on one-dimensional models of physical transport phenomena, such as system codes and sub-channel codes. And the computational cost of these models, solving these models, is low. However, the models lack predictive capabilities as they are represented by a low number of degrees of freedom. So a well-recognized system thermohydraulics code by many, that's used by many nuclear authorities for the safety analysis is the Realup 5 series. And here you see the novelization of the systems code for the primary cooling system of MIRA. So as you can see, the novelization is quite coarse. Yeah, so if you look at the upper plenum, it's like represented by about 20 nodes, and the lower plenum is even represented by a single node. So it's not very detailed, but the quantities such as mass flow rate and pressure can be calculated super efficiently basically in the whole reactor. A fun fact I think about the Realup system codes is that you have an input file and it contains like 10,000 of lines, and each line represents a single punch card. So I'm way too young to understand what punch cards are. I've never seen them. But yeah, Realup got developed in the late 1960s, early 1970s. So you don't need much of programming skills. It's cards, or punch cards. Each line is punch cards.
No.
Just for some extra information. But other than system codes, we have the 3-dimensional computational fluid dynamic simulation methods that can be used. So CFD models can contain million degrees of freedom, and the physics is more resolved rather than modeled compared to system codes. Now, once validated, they are accurate, but due to the large number of degrees of freedom, they're often feasible for the analysis of a large number of different system configurations. So here's an example of a 2-dimensional open cavity problem. So we have fluid flowing in and flowing out of the domain. And this computational domain is discretized into a set of finite control volumes. So these volumes surround like a node point on the mesh in which the variables of interest are located at the center of the control volume, and then conservation laws are applied to each individual control volume to form a set of equations that are then solved. So it's much more detailed compared to the system codes. So I put here some few examples of CFD. You probably have seen these images before, this type of images, like very colorful pictures always. For all types of industries, so not just only for nuclear. And it's good to realize that performing simulations to get these colorful pictures like requires a huge demand of computational time and computer memory usage. So therefore, yeah, what I'm looking for, and many other people are as well, is that we're aiming for the desired compromise. So namely, reduced order models that are sufficiently accurate, yet computationally efficient. So we can develop, so you get basically the best out of both worlds. And we can develop reduced order models starting from the Lund parameter models. But in my work, I only focus on this part. So I start from the heavy CFD simulations to apply model reduction in order to obtain my reduced order model. Yeah, Corona sucks. This is Corona sucks. Basically, take heart, you Ghenters. It's a message from the director of Ghent University. So Ghent University projected this message onto what they call, I think, the Tower of Books in the city Ghent a couple of months ago. And well, this is a picture of it. And according to me, it's a very strong message because, well, Corona sucks basically is what it is. So this is an image with a strong message. And if you look at the size of this image, it's like 840 pixels times 411 pixels. And so a total number of pixels are like 300,000, a bit over 300,000 pixels, to build up this image with a strong message. And you can think of pixels as degrees of freedom. So, but we don't need as many pixels to depict the core message. So I want to basically reduce this image that only contains the information that's essential. So in this case, the message, Corona sucks, how moet u Genters, that's projected on the Tower of Books. So what I'm gonna do is I'm gonna apply a technique that's called proportional decomposition. So what I'm basically gonna do is like a type of image compression. So by applying POD onto this image, I'm basically decomposing the image into a set of modes, and each mode contains some information of the image. And the modes are ordered such that the first mode contains basically the most information of the original image compared to all the following modes. So if you look here at the first mode, and you can see it's rather compressed, it only has like 1,000, a little bit over 1,000 pixels. Is that it contains the core structure of our image, but I still can't see it's really a building, let's say, or any text appearing. So if I then add also the second mode, so this is the first mode and the second mode combined, already can see it's kind of a skyscraper or building, I could guess, let's say. I add a few more modes, and you can clearly see that the text is also appearing. And if including, let's say, 20 modes, we get back to our core message. So it's not as accurate, or it's like, of course, it contains, let's say, the reconstructing based on this number of modes. The reconstruction is about 25,000 pixels, which is what is only a few percentage of the original 300,000 pixels. So in that case, this is basically what is the core of also what reduced order modeling is about. Because if you look at the first image, and now I'm gonna of the first mode, and now I'm gonna look a bit about the error we're making. compared to the original image. So don't look too much at the exact values. I don't care so much about exact values. But then I'm going to go with you through the trend that we're seeing here. So with the first image, if I compare it with the original image, I make a large error. And I don't see any text appearing. So if I add more modes, so 2 modes or 3 modes, so each of the following modes add some information, so we get closer towards the original. But you see also that the improvement we're making is all the time is a bit less if I start introducing some new modes, some additional modes, let's say. So at about 20 modes, I say, okay, well, I get to the core message. You can also see that if I would add another mode to let's say this basis of 20 modes, I add some information. I get a bit better, closer to the original, but that extra information doesn't add so much. In order for the analysis of it, let's say. So that's where I decide to truncate. So yes, I make an error with the original, and that's what we always also basically do with reduced order models. But you take that basically for granted because this will be much smaller. If you think in terms of reduced order modeling to compute compared to the original of 300,000 pixels. So in terms of reduced order modeling, this is basically what's at the basis of all the reduced order models I have developed. And I always try to make what they call an offline-online decomposition. So we have an online stage, and then we're solving the full order model. So in my case, that's CFD. Basically CFD simulations. And out of that simulations, you get what we call the snapshots. You get your flow fields or temperature fields, pressure fields, and you collect snapshots over time. Usually they're transient simulations. So you run over a certain time period and you collect snapshots in time, and then I apply POD. So really POD is applied to extract the features of my complex full order model. And then, of course, you still need to reconstruct a run because the POD modes on itself, they're not a model. It's just basically the features of your full order model. So once the reduced order model is constructed, then in the online phase, we can set a new parameter value because I don't want to solve a reduced order model for the same values I solve my full order model. No, you want to do it for slightly different values. So if you reduce order model and do that maybe 100 times, and then you don't go back between the stages. It's once you're done with your reduced order model, you want to use it. And this decomposition is necessary to keep the reduced order model process efficient. So all the reduced order modeling methods I will go through with you now is that they're all based on this snapshots plus POD approach. And what I did, I developed both non-intrusive and intrusive reduced order modeling methods. So intrusive means here that knowledge of the solver's discretization solution algorithm is required to obtain reduced order model, while the non-intrusive methods are basically backwards approaches. So if you look at the non-intrusive approach, what we have a full order data. So basically they come from a numerical simulation, but in theory you could actually also use experimental data. And you apply POD on that to get your reduced basis space. So if you think about the Tower of Books with the message is that, so my reduced basis space was then spanned, I would choose a reduced basis space that's spanned by 20 modes. And then, like I said, we still need to get our reduced order model, so we can apply some kind of identification methods to obtain a reduced order model. I will call this, for now, I will call this like an identification method. And what I worked on during my first year was like using least squares of techniques to identify reduced system matrices. So we have our full order model, and then I want to develop a reduced order model that's quite similar, but of course reduced in size. That's why we're using POD. And then basically all the system matrices at the reduced order level, I try to identify using least square approach. However, what it is for nonlinear problems is that the required number of snapshots scales with the cube of the number of POD modes in your reduced basis space. And at least as many reduced matrices are then to be identified as the number of modes used. And therefore, it is not feasible to use, let's say, my POD-based identification method for nonlinear problems. But if you look at simulations of fluid flows in engineering problems, it's necessary to also develop reduced order models for nonlinear problems. So I later on switched to intrusive reduced order modeling approaches. And actually, they're similar. The first part is similar. So we again have our forwarded data, basically your snapshots. You apply POD to get a reduced basis space that's spent by POD modes. And then I have my partial differential equations that are describing my forward model. And I project those equations onto the reduced basis space. So I get a projection-based reduced order model. And I'm not going through the whole mathematics of how to do this projection. But that's what you end up with. But this one, projection-based reduced order model, is not yet my accurate reduced order model. First, I need also some discretization, like we always have in CFD, using finite volume discretization methods. So perhaps some collision modeling, stabilization, and also importantly in my work is that the boundary conditions, if you just do the projection of your partial differential equation on the reduced basis space, the boundary conditions aren't yet included into this projection-based reduced order model. So I'll call this approach for now the project and discretized approach. And like I said, so the boundary conditions aren't necessary directly in our projection-based reduced order model. So I looked into two different methods to impose boundary conditions at the reduced order level. So we have the lifting function method, and the aim of the lifting function method is to have homogeneous POD modes. Now, homogeneous, like having a value of 0 at the boundaries of the computational domain, in order to enforce the boundary conditions in the reduced order model. On the other hand, there's like a penalty method to enforce the boundary conditions, well, with the penalty factor. And you see also, I use the penalty method over here in the non-intrusive approach. And that's also because not only I need them to impose boundary conditions at the reduced order level, but also for parameterization. So I want to run the reduced order model for new values. In this case, my parameters is basically the value at the boundary of the domain. So I need a method in order to also be able to change the value of my boundary condition at the reduced order level. So if you look a bit about the penalty factor, like I said, it's basically a way to impose the boundary condition using a penalty factor. So if this is my partial differential equation, we have a time-dependent term, and then there's a linear term, there's a non-linear term, and then I add an additional term to it, which is the penalty term. So UBC is basically my value at the boundary that I want to impose, and then I have to set a penalty factor. If you had, of course, a penalty factor of 0, I wouldn't impose anything. But also, yeah, if you choose a too large penalty factor, your reduced order model system, this still needs to be projected and everything. But that will become, let's say, ill-conditioned. So you always need to find a factor that's suitable for your problem, and that is done using numerical experimentation. I use later on I added an iterative approach such that you can just automatically do that, not manually changing values and see which one works, which one doesn't. Then the lifting function approach. So basically you have your solution and you subtract your lifting function such that all the snapshots that I have, all the forward data they have homogeneous boundary conditions. And then you apply POD, and you construct your reduced order model, you solve your reduced order model, and basically you're adding again your lifting functions, and that's also a way to impose them. So if we look a bit of the topics that I worked on, so basically for the non-intrusive approach, it was just the scalar transport function, so linear problems. Project and discretization approach, I spent a bit more time on, so for incompressible flows and heat transfer, functional turbulence as well. And today I want to look with you at one of the cases, namely incompressible flow combined with heat transfer and using the lifting function approach. So let's go back to the mirror reactor. So what we have say a nuclear core in the center, which is hot and needs to be cooled. So we have fluid passing through the core, it's heating up, and then due to, let's say, buoyancy, we have some, because due to the temperature differences, we also have some density differences in the fluid, like hot fluid is rising and cold fluid is going down. I think you all know this phenomena from the heater at home. So if you make a really coarse representation of this, we have a 2D square. One side is at a hot temperature, the other side is cold temperature, like gravity is applied. And this is just for, say, gas flow at room temperature. So what I'm going to do is I'm going to solve this numerically and then collect the snapshots over time. So I just picked 2-3 time instances, but basically I'm collecting 1,000 snapshots. So you see how the flow is developing. So hot fluid is rising and cold fluid is going down. So I have all these snapshots, and then what you can do is you apply POD. So the same thing as what I did with the image, and here you see all the individual modes. So the first modes, they more look like my solution, my final time instance. And each additional modes contain some of the information, you know, throughout the whole time period. So in the end, I'm actually using 7 modes, but I thought the pictures were getting too small at the moment. But anyway, like I said before, we need a method to impose the boundary conditions. So I use the lifting function method. So I need to set up 2 lifting functions, and in this case, they're basically fields that I'm subtracting from all the snapshots that I collected. So basically, I have one function that's related to the cold boundary. So I'm basically setting it to a value of 1 and solving the diffusion problem. And the same for the second one, because I have two separate boundary conditions, and I want to parameterize both of them, give different values of them when solving the reduced order model. So I also need 2 lifting functions. So what happens then if you apply POD on, let's say, the homogenized snapshots, is that here, so this was my original set, but I showed you if for when I just applied POD directly onto the snapshots I collected. But if I homogenize first snapshot and apply then POD for temperature, you can see, well, this grayish color basically means 0. So relative boundaries, we indeed, the boundary conditions are everywhere homogeneous. And then I do the projection onto my reduced basis space in order to develop the reduced order model. So yeah, actually to show you again, that's similar to the way I handled the image of the tau Buchs, is that I can look at the energy of eigenvalues of all the POD modes, and then I say, okay, about 7, you know, if I add another mode to my reduced basis, it actually doesn't add so much. So let's just truncate at 7 modes. We then look at the reduced order solution compared to full order solution. So snapshots I collected for certain values of the temperatures of the walls, and then for the reduced order model, I'm solving for slightly different values. And then later on, of course, I run a full order simulation in order to make the comparison. But the whole idea is to run your reduced order model for new parameter values. And then visually, they look the same. Of course, if I look at the absolute error, this is power 10 to -2. For velocity, 10 power 10 to the -3. Depends on your application, how accurate you want to be. Do you want it to be more accurate? Probably you should add some more modes or do something different in training. Of course, it depends on which snapshots you collected. Importantly, also, what it's all about is that we want to develop faster models. So the speed up, let's say, is about 20 times. Including outputting all these fields, so it's quite a gain, and the error is probably small enough for many engineering applications. So yeah, I showed you basically this method, and I showed you the one way to enforce, let's say, the boundary condition reduced order model. But this time, we saw the lifting functions that looked pretty easy, but it's usually, especially for more complicated problems, it's hard to define these lifting functions and which one will work, and they need to basically also satisfy the same physics as your full order model. But the penalty factor, it's hard to sometimes find the factor, even if you say run it automatically, to really enforce them, because if the value becomes too large in order to really enforce the boundary conditions, you get some problems. That becomes more conditioned at the reader's order level. So I will introduce now a third approach, and that's what I call the discretized and project approach. And then there's something like projection of boundary factors. So it's not an additional method to really enforce the boundary conditions, but what we'll see will become clear in the next slide. So the principle is the same, because it's an intrusive approach. So we start again from forwarded data, apply POD to get a reduced basis space. And then we have our partial differential equations. So rather than projecting our partial differential equations directly onto the reduced basis space, we're now first going to discretize them. So we have a discretized full order model, basically consisting of full operators, and also a vector that's containing the contributions of the boundary conditions. And that's what I then project in order to get an accurate run. So basically here we needed to do an initial step of discretization posing boundary conditions as well. That's all included basically over here. So we go straight to accurate reduced order model. And basically this approach and like dealing with the boundary conditions is one of the benefits of first discretizing, then projecting. But that's basically what I did during this 3 months that I didn't spend so much in the office. So I worked on laminar flow, so not yet on the most complex problems. And then we'll show you now this case of a lid-driven cavity. So the lid-driven cavity problem, if you're not familiar with it, is basically, so this is a 2D problem. It's again a square. Here we have some walls, and we have the lid is moving with a constant velocity. So what you get is that flowing, so this velocity magnitude, so everything is basically positive. Is that the flow is moving a bit into this direction. So this is like a steady state solution. We got some recirculation, so it's over here. So I'm not gonna look, I want to show you a bit of the results and the error basically that we're making. Because really this order modeling is always the trade-off between the computational gain and the accuracy. So if you can see here, so it's the relative error for velocity and the relative error of pressure, and velocity and pressure in this case. For this problem, they're coupled. So I used a basis of 2 modes up to 20 modes. So for 2 modes, you can see the relative errors, let's say the error I'm making compared to the full order model. So I didn't do any parameterization. Basically, it's for the reader's order model is run for the same setup as for the full order model, for which I collected the snapshots. You see it's relatively high error, and so I need to add some more modes to reduce the order. And then at some point you probably say, oh, well, it's acceptable for my case or not, or you said. So this is a clear trend that the more modes you're adding, the more accurate your reduced order model becomes. You see also some dotted line. Basically, that's what we call the basis projection error. It's the best possible error you can get at every time instance, and this error is resulting from truncating the number of POD modes. So basically that's what we also did with the pictures. I didn't have yet my reduced order model. I truncated, and then basically just showing what's the error we have compared to the original, and the same trend is visible for the pressure. Then let's have a look at a bit of the computational time, because it looks nice, of course. We can add a lot of modes to reduce bases to get a more accurate ROM, but you also see it becomes more expensive. So the red line is basically the amount of time it takes for my full order model to be solved. In order, I need some full order solutions in order to apply POD onto the snapshots. So that's in the offline phase. Then I need to apply POD. So that takes some time, and basically that scales linear. So if I need more modes, I'm not solving for all the possible modes, basically just for the ones that I need. So if I add some more modes, it takes a bit more of computational time. And then you need to, basically calculate reduced order matrices that are forming your reduced order model. You can see that this is clearly not linear, because for this problem it also contains the nonlinear convection term. So then indeed, as soon as I add more modes, this time goes up. However, this is still in the offline phase, so it can be quite reasonable to still add some more modes just to solve for my to get my reduced order model matrices. However, this is all offline, so we want to only do that once and then basically solve the reduced order model. And that you can, I didn't do it here, but you can solve basically the reduced order model for new parameter values. So in the end, because you only do this once, it's good to look at how much are you gaining, let's say, for the green one compared to the red one. So how much time it takes for the reduced order model to get solved and for the full order model. And then you can see indeed, let's say this is speed up. So the less modes I'm adding, the faster my reduced order model is in comparison to full order model. But based on this, it's hard to say on beforehand how many modes you're going to need, because you need to know what kind of accuracy you're looking for, but also at some point, like adding too much modes is not gaining you so much. So a short recap about what we have seen. So we have seen three methods, like identification, which was a non-intrusive reduced order modeling approach, and then two intrusive reduced order modeling approaches, the project and discretized, and the discretized and project approach. The nice thing about non-intrusive reduced order modeling is that they're independent of the high fidelity solver algorithm. So it's really a backblockers approach, and well, here you really need to know what's behind it. Let's say for your discretization of partial differential equations. We saw some methods to enforce boundary conditions to reduced order model. So both to actually have them in your reduced order model, but also in order to be able to change them such that you can run your reduced order model for different parameter values. And then finally, we saw the one I developed together with Benjamin in last spring, using, let's say, projection of boundary factors in order to not have the lifting function approach or penalty method approach. So all the reduced order models or the cases I showed you, they're quite efficient in terms of computational time and storage, because we have an offline phase, online phase that are decomposed. And there's always a trade-off between accuracy and gain in computational time when working on reduced order modeling methods. So for the ones interested on doing this yourself, I also worked with another group. It's called CISA Advanced Lab. It's an Italian group in Trieste. They're developing and I'm contributing to that, to the development of Ithaca finite volume. So it stands for in real-time highly advanced computational applications for finite volumes. But basically this contains also many tutorials on how to develop a reduced order model for, let's say, for the project and discretized approach, but also now adding the discretized and project approach to this. And it's open source. It's on GitLab, so GitHub, so you can have a look. This was my presentation for today.
Well, thank you, Kelbij, for a nice presentation. If anybody has some questions, you can unmute and ask. If not, oh, yeah, go ahead.
In the beginning, Kelbij, you had penalty factor in a method which you, I think, finally did not. You go for the lifting approach, isn't it?
Yeah, for this, for the specific case I showed, I used the lifting approach, but I use both in my work and compare them as well.
Yeah, and for the penalty factor, you said it's not a trial and error approach you have there to determine it. You do have some theory.
Yeah. Okay. Yes. Like what they usually do is, yeah, you try everything between between 0 and 1,000,000 or so, and see what enforces your boundary condition or not. That can be done manually, or you can just like use an iterative approach, so just a first order iterative solver, just to see, okay, if I lower my penalty factor, is it still enforced, or if I higher it, yeah, if your solution, let's say your reduced order model solution becomes unphysical, then yeah, okay, you might enforce your boundary conditions, but yeah, it's not, then the factor is still high. So that's therefore also in some cases you cannot find a suitable factor.
And so this approach, which is rather heuristic, say, is it also the case for the lifting function approach?
Yeah, no, the lifting function approach is more physics-based. So you need to take into account, for example, that I'm working with incompressible flow. So your lifting function is more or less also like satisfying the continuity equations, for instance. It's usually if you have only one function to set because you have only one non-homogeneous boundary condition, it's already easier than if you have to set two, because each time you're subtracting also a field from all of your snapshots, and if you have to do that multiple times, yeah, still your snapshots also physically should still make sense, and therefore it becomes not always not evident to come up with a suitable function. So yeah, therefore, yeah, that was good that the project I did with Benjamin is like, okay, let's go back to more simpler cases, because I was of course developing reduced order models that were getting more complicated, and you know, adding heat transfer and adding turbulence, and get back to the basics and see like, okay, what can we do to, for example, yeah, not having to set a factor or come up with the function, because that makes it, if you don't have to do that, it makes it more generic. It makes it more engineering proof as well. Also in the end, yeah, the results, they become also therefore more accurate, because everything you have to tune yourself, also introducing some additional error. And the reduced order models are quite sensitive to errors.
If you have simple boundary conditions like, I don't know, use 0 everywhere on the domain, isn't that contained in your modes already, in your PUD modes?
No. Yeah. Okay. So if the boundary is 0 everywhere, well, what you can say is that the PUD modes, basically PUD modes are a linear combination of snapshots. So you can say, oh, my boundary conditions also, if they're contained, let's say, in the snapshot, they will be a linear. In the modes, there will be a linear combination of the boundary conditions of the snapshots. The problem is if it's homogeneous, and that's why you're starting lifting functions. The homogeneous is 0, so any linear combination will lead again to 0. But if it has a value that's different from 0, well, yeah, then it can be any linear combination, and that's why that's why I say, okay, they're not enforced in the reduced order model automatically, because, well, if you just solve the reduced order model, they literally have any linear combination of values, let's say, and then of course, yeah, your reduced order model blows up almost straight away.
I also have a question. Thanks for the interesting presentation. I was wondering, you showed that you also did some research on turbulence. how many modes do you then need, or does it still work quite well then?
Yeah, that's an interesting question. So it's not necessary in terms of mode where you get issues with turbulence, because actually the case I worked in turbulence, I wasn't collecting snapshots in time, I was collecting snapshots in parameter space, so there were steady states, basically all steady state solutions. But even if you do it in time, yeah, you probably need a few more. But if you have a CFD problem that contains millions of degrees of freedom, like you still, even if you would need 100 modes, it's still a big gain. But yeah, with turbulence, usually what you have is you have at full order level, you also have to solve equations, turbulent transport equations, and basically some closure modeling. That's always the case. Also with turbulence at full order level. And that's something you also then need to do at reduced order level. So what you do, usually what we try to avoid is to also start projecting turbulence transport equations onto reduced basis spaces, because yeah, the problem gets, you have more, let's say, variables. That's why you have the additional equations, but also at reduced order model becomes complicated and to get really closure. The only thing is with turbulence, it's always what you have to take into account is that we're truncating. So I'm only including the first number of POD modes. So if you look at turbulence and you look at the energy cascade, actually, let's say all this dissipation is more or less contained in the smaller of the higher POD modes. Right, they have less energy, but therefore they're in the. So basically, the first modes contain the bigger energy scales, and then the higher modes, they contain the smaller energy modes. But you're truncating it, and of course, everything that you truncate, yeah, you cannot solve the reduced order model for, because that information is then not contained in your reduced order model, and that's why they usually, yeah, it becomes more complicated at solving for turbulence. But the number of modes. In my case, I was still working even with 5 or 8 modes for velocity and for temperature. So not from that perspective.
You still need a turbulence model if you truncate.
Yeah, so what I did and what you see happening a lot is that I'm not going to use the same turbulence model necessarily as you do at full order level, but rather, let's say, use data-driven approaches to, like I do also in the non-intrusive approach, to identify, let's say, some of the variables that are essential for the turbulence part. So let's say your eddy viscosity term is something that you then approximate using data-driven approaches, and then solve the reduced order modeling using, let's say, the intrusive approach. So in that case, you don't have to project also the partial differential equations, let's say the K epsilon equations or whatever. Yeah, so you use a combination of, let's say, intrusive and non-intrusive. Makes it more practical as well.
Hi, thanks for the talk. I was wondering if you could go back to slide 25, if you could explain the wobbles in time that you have there, depending on how many modes you have.
Yeah, okay. This one, I think, right?
Yes, exactly.
Yeah, it's a good question, because I always also wondered, and I still don't know so much what's causing, or if you can say, oh, because I'm using so many modes, I'm gonna get so many. The frequency of let's say my output solution will be this. You always see it depends also on the. It doesn't really depend on the time I'm running the reduced order model for. So if I would run this even for 2 seconds, you will see this, basically this gets more stretched. It's not that it repeats or so. Yeah, I still don't have a good answer to that, why that is the case. Yeah, mostly looking at the trend. So yeah, of course. So if you look at this, because it's this bubbly, is that that at some time instances it might be a little bit more accurate than for example this time instance. But yeah, in general, it's of the order 10 to the minus 7, I think. Yeah.
So it already appears for your basis projection error, and the best approximation you can get with your PUD basis. You already see this behavior. So it is not related to the reduced order model. It is related to the SVD probably.
It's yes, exactly. Yes, it's for the dotted line. So basically, that's just the error for the truncation of the PUD modes. It's the same behavior. So yeah, it's not reduced order model related. It's PUD related.
Yeah.
So these are still fairly.
Could you maybe say something about? So you showed one case. Oh, sorry.
No, go ahead, Benjamin.
Okay. You showed one case where you had the parametric study, but you slightly changed the parameter value. I think with the hot and the cold.
Oh yes, wait, I'm gonna look for it.
Did you try larger perturbations?
This one you're talking about, right?
This one, yeah. So it's 0.3 Kelvin difference.
Mm-hmm.
Yeah.
So I did.
Exactly.
Okay. So for this case.
The difference. Yeah.
Yeah. So for the snapshots, I just the boundary conditions are not are steady in time, are constant in time. Let's say. So I'm just running one transient simulation for these values at the boundary, and then indeed the reduced order model I did for this case, but and then they're not necessarily. So this is the difference is 0.2, this difference is 0.3. But also if you just say okay, an equal difference on both sides, or out, let's say also values. Also, what happens is that what's easier to do, because the reduced order model is only trained for one parameter set, only for this one, you need to stay rather close to your original value, because this is a buoyancy driven problem. It's a highly non-linear problem. So it also means that if I choose, and let's go towards the extreme case, if I run a reduced order model or a full order model to collect these snapshots for these values, and I would then want to run my reduced order model for a case where I have, let's say, a cold temperature that's equal to my environmental temperature, and then we just have a hot side. What will happen if you just have a hot side? You don't see this flow. You just see basically fluid is rising at the hot side, and it's not that it's cooling down so much on this side that it's dropping. So you get a completely say different flow field. And now I'm training, let's say, using this type of solution, so that even the flow field for this side is more or less contained into my POD modes, and I can use my reduced order model to solve that. But let's say if I use a snapshot just for the case where I have just one hot side, then basically what's happening here on the cold side, well, that's not contained in my POD mode, so my reduced order model won't be able to solve for that. And therefore, because it's quite a highly non-linear problem, stay relatively close. If you work on let's say linear problem, more towards a bit less non-linear problems, you usually can go to a wider parameter range. But the solution would be, of course, to include more snapshots of different parameters in let's say, to train it for. But there I will always think about like for what do you need your reduced order model for? If it's just for a few values and I need a few sets to collect snapshots, then it doesn't make sense to develop a reduced order modeling using, let's say, 5 sets of snapshots. But if you need 100 or 1,000 simulations and all values between, I don't know, within a range of a few Kelvin, then it could be, it could make sense to just enrich your training space. Also, in this case, it's a hard case. It's buoyancy driven. There's no forced convection. So I also don't want to go to too high differences between temperatures to not go into turbulence and to keep it on laminar. Yeah, but that's why. So it's relatively small, but it's a gain of 20 times. So depends how many of them you need to do.
Great, thanks. Yeah.
Any last questions for Kelbij?
I have one question. So are you, because these are time-dependent problems also that you consider, now over long time intervals, for instance, the flows may sort of evolve towards a different regime where you'd need a different set of snapshots to capture that. Is that something that you're thinking about? Is that something that's relevant for the problem that you consider?
Yes. Okay, so indeed, actually everything is about when working with POD. So if it's not in your snapshot, it's not in your reader's order model. So if you indeed would solve your full order model for a certain problem and you end up your snapshots are in a certain regime and you want to solve your reader's order model for a solution that appears in a different regime, then you can't use your reader's order model for that. What you're saying is that, okay, but if I set up a reader's order model, let's say for one part of the regime and then another reader's order model for another part of the regime, it's certainly something that is done. What you can do is, especially if you work on in let's say a larger parameter rates, is indeed you just not develop one reader's order model that can handle it all. You develop several reader's order models, and depending on then where your parameters appear in a certain regime or another regime, you take that reader's order model. That's
actually, I was more thinking of situations where the parameter stay the same. It's just that the flows are by itself changes character. So it may seem that maybe over a limited time interval, you can do with a fairly small number of POD modes, but then you also capture this evolution towards a different type of flow. You would need many more POD modes.
Yes. So what you often see happening, for example, also at the beginning of simulations that start from let's say a zero flow field, that during the beginning of your time interval, let's say the flow is chasing the fastest compared to later on in your simulation. And what you then need is, for example, you need to collect more snapshots in that time period. So if you really want to set up a reader's order model that is valid for first the flow that is actually in a laminar regime and then in a transition regime and then also becomes turbulence throughout the whole time interval, your reader's order model won't be accurate for all of the regimes. So in that case, it's better to develop reader's order models, for example, for the part that's in the laminar regime, and then basically use then as an initial consideration for your second reader's order model for the transition regime, basically your final solution of your first reader's order model, and so you can work through it. It's always better to confine, how do you say that, to put, let's say, all the characteristics, to not try to include them all, but have it specified for certain characteristics. Then the POD, let's say, will be also the strongest. And you can develop different readers on order to catch different.
Okay. Thanks.
Any last question, maybe? Otherwise, I guess we've been going for an hour. I guess we can adjourn. So thank you, Kelbij, for the nice presentation.
Oh, thank you for your time. It's a pleasure.
Thanks a lot.
Yes.
And good luck with the next defense.
Yeah.
Yes. 3 weeks. Yeah.
Yeah. Success with that. Thanks.
Bye.
Bye.
Bye bye.
Bye.
Bye bye. Good luck.
Thank you.
Good luck. Bye bye.